Welcome to this session. This is Narayanan Ramanujam. I'm going to present about simulate your rubber products using MSc Marc's advanced nonlinear FEA solutions. So for the rubber products, we have two softwares. One is the MSc Marc and one is the MSc Nastran Sol 400, which can take care of your advanced nonlinear FEA solutions. So today's agenda will be to discuss about the rubber design and simulation overview, rubber material models and data fit capability. So we had in the previous session discussed about the rubber testing using like uniaxial extension, biaxial extension and planar shear. So once you have this testing, then you can do the curve fitting using the Marc Mentat user interface. And once you do the curve fitting, then you get the coefficients that you have to use for the various material models. For example, Aruda Boys, Mooney Rivlin, Ogden. So whatever you want, you can actually calibrate those test results and get the coefficients and give it for a FEA simulation. We would also like to talk about some of the other technology differentiators we have for the rubber material modeling. You can model also the heat generated because of the loading and unloading. There is a hysteresis that happens in rubber, and because of that, there is heat generated. So you can actually simulate the heat generation. You can also take into account the damage due to the Mullins effect because you're unloading the rubber after a few cycles because of the breakage of bonds. There is damage. So you can use this Ogden Roxburgh damage model to calculate the damage in your rubber products. Also, you can do the crack growth simulation. For example, if you have a product that is going to undergo cracking, so you can simulate the cracking as well using MSc Marc. So you can also do the adaptive remeshing. What we mean by that is that you can have a coarse mesh. So one of the first activities that you have to do in FEA simulation is after you get the design, you basically create the mesh. So the user can create a coarse mesh, but during the course of simulation, it can automatically remesh it so that you can get with fine mesh in the region that you want to create a fine mesh. So there are two techniques we have. One is called the global adaptive remeshing, and the other is called the local adaptive remeshing. And with 2021.4, which is our latest release for MSc Marc, you also have the rubber fatigue capability. So you don't just get the stress and strain results, but for mechanical fatigue, for certain applications, you can get the fatigue results as well. So if you want to plot the damage or the life cycles that your component is going to see, you can plot that all within the Marc user interface. You also have the co-simulation capabilities. So these days, people are interested not only in performing the structural simulation, but they also want to couple the structural simulation with, say, like fluid simulation, for example. So one example is the rubber seal models to check for leakage, for example. Or you can also couple our product with MSc Adams, which is the leader in terms of modeling multi-body dynamics. So you can couple Adams along with Marc to create like a kinematics to structural simulation. Some examples of this is the car door rubber seal that we have performed for customers such as Standard Profile and Tata Motors. So then I will leave you with a bunch of case studies that we have for the rubber industry. So rubber design and simulation overview. So rubber is used across multiple industries. For example, it is not just used in the automotive domain, but also aerospace, machinery and defense, biomedical, electronics, etc. It's used because it's widely available, it's low cost, and its properties are customizable. So you can actually tailor the properties of rubber by changing the compounding methodology or technique, underlying compounding technique. So applications-wise, if you talk about the automotive industry, then it is used for rubber seals, engine mounts, suspension mounts, rubber boots, wipers, tires, etc. So we have customers in various space. So for rubber seals, we have certain customers. For rubber tires, we have customers from the heavy truck, heavy tire industry, so on and so forth. But not only for the automotive, but you can also see for the other industries, like some examples of the rubber products. Like for aerospace industry, you have seals, mounts, tires again, ducting, seat belt, and padding, which are all made out of rubber. Again, simulating rubber has a lot of challenges, so it's not straightforward. So there are various challenges that are there. So material property related challenges, design challenges, and simulation challenges. So when we talk about the material property challenges, you know that the rubber can be elastic. It can see like very high amount of strain, beyond even like 100% strain sometimes. It also exhibits like nonlinear elastic stress strain behavior. It's nearly incompressible. So in the previous presentation, you saw that the Poisson's ratio is 0.5. So there are certain difficulties associated with modeling rubber because it's nearly incompressible. There is also temperature dependency. In filled rubber, if your temperature increases, the material behaves soft. So at room temperature, it has a certain property, but then if you change the temperature, its storage modulus and loss modulus or the properties change with respect to temperature. Not only that, there is also time dependence. For example, if you do a stress relaxation test or a creep test, so the properties change with time. So if you just hold the rubber there and then let it sit there, then it undergoes creep or extension if you just let it sit there. So you have to be able to incorporate the viscoelastic and viscoplastic effects as well. It undergoes damage and failure also. So it's pretty challenging to incorporate all of this material property behavior. Not only that, the design challenges would be like if you want to install the rubber seal, what are my installation forces? Also, you want to install the rubber, when you're installing the rubber products, you want to make sure that the force, that the component sees is minimal. Also for rubber seals, the sealing effectiveness is important. So you want to make sure that there is no leakage. So the sealing is effective in short term as well as long term. In terms of vibration isolation, for example, if you're talking about engine mount products or suspension mounts, in case of engine mounts, you want to isolate the vibration so that the vibration does not get transferred from the engine to the other components. So for that application, also rubber products is very useful. Also, it is important to be able to simulate the rubber product in hot conditions as well as cold conditions. In cold conditions, the rubber almost behave like a very brittle material. So there is change in the material properties with temperature as well. Simulation challenges. So to incorporate all this material property challenges, you have to make the material models. To incorporate the behavior of large strain and extensive amount of deformation, you have to make the element formulation has to be robust. And then if you have like an assembly that is made up of different rubber components, you also want to take care that there is extensive amount of contact. So there can be like multi-body contact or self-contact. The rubber can contact with itself or with other components. And also the friction behavior in rubber is very complex. Sometimes you can give a specific coefficient of friction value, but sometimes the friction also depends on other factors like sliding velocity and contact pressure. So you have all these capabilities within the MSc Marc product that we have. Okay. Marc is a solution for your tough nonlinear problems. It was the first commercially available nonlinear FEA solution as early as 1971. Beyond that, it's about like 50 years of subsequent releases where there are constant improvements that is made. So it's a leader in terms of solving complex problems. There is 3D contact. You can have parallelization. You can submit your job to multiple CPUs or GPU, also like graphical processing unit these days. Automatic remeshing. So during the course of simulation, you can either choose for like a global adaptive mesh or a local adaptive mesh. You can also perform failure analysis. So it's a general purpose nonlinear solution that's suitable for highly nonlinear materials. You can have large strains and deformation. And it has a easy to use contact interface. So with a couple of button clicks, the user can actually set up a contact analysis. One is detect mesh bodies that detects all your contact bodies in your model. And then using the contact table, you can actually automatically populate the contact pairs that is going to come into contact during the course of simulation. It has a broad industry presence like touched upon in the previous slides. Then I'm going to show you a few videos of the rubber simulation. So this is bushing. This is a washing machine seal. This is a packer seal that's used in the oil and gas industry. It's a ball joint boot where you can, where the rubber product can undergo extensive amount of deformation. That can be self-contact or contact with other rigid bodies. This is one of our, more popular workflows where the glass door, for example, this is an automotive door seal where the glass rod is penetrating the rubber seal and then going back. So here the users are interested in finding out what is my installation force, where insertion force, where is the extraction force. So it's an example of shifter boot where there is extensive amount of contact, a seal where there is actually like adaptive remeshing. So once the rigid body pushes against the seal, there is going to be automatic remeshing here. Okay. There are more videos and more examples. So if you're interested, we can share that with you. So the second topic, one was about the overview of the design and then what capabilities we have. The second topic is the rubber material models and experimental data fit capability that we have. So as touched upon very elaborately in the previous presentation, you would have seen that for characterizing rubber completely, you have to test the rubber product under simple tension. So you have like a specimen, like a dog bone specimen that is fitted onto the Instron machine, and then you're pulling on it. So this specimen will undergo uniaxial tension. So then you test the material to get the stress and strain behavior. So we are showing true stress versus true strain. So once you test this product in Instron, you get the engineering stress versus engineering strain. Then you have to convert it to true strain and true stress, and then get this graph. Okay, before you feed it into the FEA simulation. So then the second is the biaxial extension, because it is tough to test the product under compression, because the response is going to change with respect to friction. So what you do instead is that you subject this rubber to biaxial extension, so that in the third direction there is compression. So biaxial extension is nothing but a compression test, and then planar tension, then that is corresponding to the shear test. So it is recommended that you test your product under all these three conditions. So in case if you're not able to do that, we at least recommend that you do a uniaxial extension, but it is better to have all of the testing done. Then this is a slide that is there for sample curve fits. So not only for the hyperelastic materials, you can also actually fit, for the, the volumetric data, or with or without the volumetric data, or you can also do it for the damage. So for example, if you have like damage associated with the rubber product, that can be captured using the Ogden Roxburgh damage model. So if you have like viscoelasticity, time-dependent behavior, that can be captured, or what we mean by plasticity is the permanent set. So if you load the rubber and then come back, then it doesn't regain its original shape. So in this case, the permanent set can be modeled using the viscoplasticity approach that we have. So it's an example of different curve fitting that we have done using the Marc Mentat user interface. So if you have any queries related to that, you can reach out to me, and we can help you do the fitting once you have the test data from a test lab. So moving on to the next topic, it's heat damage and crack growth simulation. For example, if you have like a damper model that is subjected to harmonic stresses, so you have like loading and unloading, so you have like a harmonic loading that is going on. Because of this, there is hysteresis of the product, and because of the hysteresis, there is heat flux generated. And once you give the heat flux to the thermal model, then you can get the temperature distribution in the model. So such effects can be captured using MSE Marc. It's an example of a damper model which is subjected to harmonic stress, which is a structural model. Once you have the structural analysis completed, then you can chain the simulation with a thermal simulation. So in Marc, you can either do a chain simulation, so you can do the structural analysis first and then a thermal analysis, or you can also couple the different analysis to do a structure thermal coupling, basically. So this is a structural simulation. So at the end of it, you get the stress and transfer the heat flux because of the hysteresis to a thermal model, and because of the heat flux as the input, then you can get the temperature distribution in the product. So you can simulate the structural as well as the thermal response of a rubber product, which sees like repeated loading and unloading. Okay, so the previous presenter also touched upon the Mullins effect. So if you're actually loading and unloading, so there is breakage of bonds and then damage because of the Mullins effect. So this can be simulated using the OR damage model that we have. So this is an example of a Jounce bumper that you have a particular loading sequence. So you can see that there is multiple cycles where you're loading and unloading the product. So you're applying a compressive force and probably releasing it. So that can be an example. So when you're subjecting it to cyclic load, then you have like damage accumulated during loading, and you can actually plot the damage results as a function of the cycles or time in this case. Okay, so you can replicate the damage effect using the OR damage model within MSE Marc. So another topic of interest is the crack propagation. So some of our customers are interested in actually finding out how the rubber products crack. So for that, we have various techniques like the VCCT or the virtual crack closure technique, or the J integral approach, or other popularly used, cohesive zone approach that is used in the industry for being able to simulate the crack in rubber as well as steel products. So to be able to capture the appropriate physics, you want to know whether a given crack is going to grow. So you can have a priori crack defined, and then depending on the loading, you want to actually simulate the crack path. So not only that, you can also see that you have like a particular mesh that you start out with, but during the course of simulation, the crack has refined itself. So the crack is changing, and then the crack tip is also changing. The path of the crack is also changing. So this can be captured. So you can also give like fatigue type loading or a direct load. You can also simulate the crack bifurcation in case if you have like one crack and if it is going to bifurcate into two cracks or many cracks, that can be captured. Crack initiation can also be simulated. So if you don't know how, if you don't have a crack in the model, and then you have certain criteria, say like for example, if the stress is exceeding a certain limit, then you want to create the crack. So you can create the crack and then model the multiple cracks as well. And then you can have your own user defined criterion for crack. So heat, damage due to Mullins effect, and crack propagation can all be modeled within MSc Marc Mentat product. So one of the other technology differentiators we have is also the adaptive remeshing. There are two approaches. So global adaptive remeshing and local adaptive remeshing. Local is where you have a certain local region where the strain or stress can exceed, and then the user can come in and say that if the strain exceeds this value, go and adaptively refine the mesh. So you're starting out with a coarse mesh. In this case, the rubber is getting squeezed in between the mandrel, and then you can see that a fine mesh has been created because the stress or strain is exceeding a certain value. So you can see the fine mesh here, right? So similarly for the packer seal as well, for the oil and gas industry, this has been applied. Rubber cutting application or metal cutting application, or in case of crack, where the crack tip is moving, you want to have a focused mesh that is created. So when the crack is moving, you can see that the focused mesh is also moving in this case. So these are some of the examples of local adaptive and global adaptive remeshing. We have various approaches to incorporate this. So if you're interested, again, please reach out to us. So in the recent releases, 2021.4, our latest release is 2022.1, which is going to come. But in the 2021.4, as well as early as 2020, we have this rubber fatigue capability, which is undergoing constant improvements. So with this, what the user can get is that not only can you get the stress, strain, or displacement results, then you can attach it to a fatigue curve, and then give the fatigue properties for the rubber, and then the user can get the damage, the extent of damage that is happening in different regions. For example, this is a notched dumbbell specimen. Because of the notch, then you know that the stress concentration is going to be near the notch, and then you can plot the damage as well as the number of cycles the component is going to last in different parts of this model. This is also an example of an engine mount where there is axial and radial loading. And then in this case, you can plot the fatigue damage and then the fatigue cycles that the component is going to last. The user can give like a constant amplitude load or a variable amplitude load. And then in case of the random load, then the software will use the rain flow counting approach internally to calculate the fatigue number of fatigue cycles and damage in this case. So this is undergoing a lot of enhancements, and we have few customers in India that we are talking to that are using. So if you're interested in some use cases, we can share them to you as well. So that's some of the technology differentiators we have with respect to MSc Marc. Okay. Not only that, you can also couple what you get with MSc is that you have this scheme called MSc 1. That is a lease-based scheme where you can actually get a pool of tokens and then launch the product of your interest. You can launch Marc or Nastran for the structural simulation, or for the CFD, you can actually launch, for example, Cradle, or multi-body dynamics, you can launch Adams. So the strength of Marc is that now we are interfacing with different products that we have in-house to create the so-called co-simulation. So you can either go with a single physics. In case of single physics, that means like a standalone structural or thermal analysis. One example is the stretching or compressing of a rubber component to get the strain or stress. Whereas if you're applying a heat flux in an automotive fuse box or a rubber component, again, like an engine mount, to get the temperature distribution, that's a standalone thermal simulation. That's a standalone thermal simulation which captures only the single physics. If when you're talking about the chain simulation, then it is, you have performed structural analysis, and then at the end of the structural analysis, then you're actually going to invoke a thermal simulation. So that can be an example of chain simulation. So you call one program after another, which becomes chain simulation. Bespoke open coupling is automated, relatively better coupled simulation using third-party interfaces. Co-simulation is something that you have closely coupled simulation, which you can actually couple product like MSc Adams with Marc, or Marc with CFT product like Cradle, which basically lets the two applications talk to each other and update the response. So it's a true multiphysics. This allows you to capture the holistic performance of a product. There's increased accuracy and precision. Because you can capture the details of the particular component that you're interested in. It allows for faster analysis, because if you're talking about an assembly, you can model the rigid bodies using MSc Adams and then focus in on the product of interest using MSc Marc. So it's readily available. You can use the MSc One pool of tokens and then invoke any of our MSc products. It's unique because we are offering the co-simulation advantage to you. So it's an example again of a model. So MSc Apex is the unified CAE environment. So you can actually create CAD models and mesh it using the MSc Apex, and then you can create an Adams. So your multi-body dynamics team can create an Adams model where you have all this, the body in white components modeled in Adams, and only the tire, or in this case, the lower control arm, which is the region of interest in MSc Marc. And then the Adams passes on the force information to Marc, and Marc passes on the, Adams passes on the position information to Marc, and Marc transfers the forces back to Adams. So in this case, you can couple both the Adams and Marc simulation to get the response. And then you can see it either using the Mentat user interface or Adams GUI, or say like a common platform like CI Insight, where you can see both the Adams result as well as Marc results in one unified GUI. So we have various use cases and case studies for the rubber products as well. So one example is the car door seal that we have performed for Tata Motors. So a washing machine rubber seal that is performed for Samsung Electronics. So if you're interested, you can go to this website. There's a number of case studies that are available. So you can see some of the customer testimonials on this slide, basically. So that's a brief about what technology differentiators we offer with MSc Marc for rubber products. Okay. Moving on to case studies. So this is one of our recent case studies that was done for Ferrabine. So here in this case, after designing everything, basically the customer then found out that the train in this case was having a low lateral stiffness. Because of this, the carriage was swaying from in the lateral direction too much. So they wanted to adjust the rubber stiffness. So they simulated this rubber to metal bonded product using MSc Marc. So then they adjusted the lateral stiffness, or increased the lateral stiffness in this case. Then they could actually reduce their testing time, because what happens is that if you are going to create the prototype and then going to test this for the lateral stiffness, that can increase your cost, because you have to make multiple prototypes and test it. So you're able to reduce the testing time by about 50%, and then also the material costs associated with creating multiple prototypes can be eliminated if you're actually performing simulation. So an example of an advanced non-pneumatic tire. So these days, the tire industry is moving towards creating non-pneumatic tires, in the sense that there is airless tires. So Michelin has its own Twill, Goodyear has its own non-pneumatic tire. In this case, it was done for big tire, where you have like a central hub, and then there are spokes that are connecting to the outer tread shear band. So this is a complex structure where you don't have air that is filling the tire cavity. So in this case, they were interested in finding out what happens when the tire rolls over a cleat or an obstacle, for example, and then get the force displacement behavior. So that we could capture. Also, we have several customers in the tire industry space like Bridgestone, Goodyear, and then in India, we have Ralston and other customers that are using MSc Marc for their, tire rim mounting, inflation, deflection, 3D deflection, steady state rolling, for computing rolling resistance, which is a measure of fuel efficiency, and various others, basically. It's an example of Parker Hannifin, where it's an underwater, deep water for deep water oil rigs. They had to use a seal and they had to replace it. And then the MSc Marc was able to capture the behavior of this underwater seal. Then they could solve and get an understanding of the mechanics of what happens in seal and replace the seal with virtual simulation, basically. It's an example of a rubber boot product where you can see that on the left side, they're using a lot of material. And then after doing the simulation using MSc Marc, they're able to cut down on the material. And then on the right is the result of the simulation for the CV boot. So they had to use only this much amount of material. So because of that, they had a huge material saving. It's an example of CV boot product that they've used MSc Marc. So the customer in this case is Race-Tec. Again, for Dura Automotive, you can see that there are some clear areas which the simulation was able to capture. In this case, that there is high amount of stress or strain concentrations. So this was captured in our product, and then using MSc Marc, we could perform a design study. Several designs have been tested virtually, and then they were able to narrow in on a boot design that were able to meet the tear strength requirements in this case. It's an example of a product where you have an inflatable dam that you can actually inflate the rubber product. So the challenge here is that it's not just made out of rubber, but you have like nylon cords reinforcing the rubber product. So in this case, we were able to simulate the rubber product with nylon cord reinforcement, and this undergoes like multiple environmental factors. It is in the water, so you will see have water pressure, the temperature would change. So all those behaviors had to be incorporated, and then simulations in this case is going to be the only way for them because they cannot make a prototype or a huge dam. So they had to completely rely on the simulation to give them accurate results. So physical prototype was not possible in this case. And they were also able to get an improved knowledge of this kind of flexible structure where there is nylon reinforcement inside the rubber. So this is an example of, again, ball joint boot for GF Lemforder. So in this case, we were able to compare the predictions from the MSc Marc and line it up with the test results. So this is a test fixture, and then this is a simulation, and then we were able to see that the load versus deflection was coming in close comparison with the test results. So it's an example of a ball joint sealing boot that was done for GM Lemforder. So these are the various case studies we have. I mean, of course, we do engage with customers very actively. So in case if you have like further queries, please reach out to us. Please reach out to me at the email ID that has been provided to you. Thank you for giving me the opportunity to discuss and present to you the capabilities of MSc Marc applicable to rubber products. Thank you very much.